In this video, we're going to talk about pH, how we calculate it, and what it means. So the pH scale is a logarithmic scale, and it represents how acidic or basic a solution is. So if we look at this image, we have pH in the first row. It runs from 0 all the way up to 14. It's the standard scale anyway. Anything that is less than 7 is considered acidic. Anything greater than 7 is considered basic. This word alkaline is another word for basic. What these numbers actually represent is the hydrogen ion concentration versus the hydroxide ion concentration. Now these concentrations are very small numbers, so notice our scale here runs from 1 down to 10 to the negative 14th, and the hydroxide's the opposite, 10 to the negative 14th up to 1. So to more easily understand these numbers, we convert it to a logarithmic scale. So we're dealing with 0 to 14. The other thing to notice is that these two concentration scales are flipped. So if you have a lot of hydronium, so you're down here where your hydronium concentration is high, you have a low hydroxide concentration. Now you're always going to have both in solution, and they have to balance out. So if you have a low hydronium, you're going to have a high hydroxide concentration. Here's a few common items and where they fall on the pH scale. So we have HCl, which is a strong acid, has a very low pH. Battery acid has a pH of less than 1. We have got lemons, vinegar, both around a pH of 2. Tomatoes are also acidic, a little bit higher though, about 4.5. Rain actually has a pH of about 5.5, and we'll talk about that later in this chapter. Milk, pretty close to neutral, but at about 6.5. Pure water should have a pH of 7, which we consider neutral, but it does have to be pure. Eggs, baking soda are both slightly basic, and then you start getting into cleaners and things that we tend to not consume, soaps, ammonia, bleach, and so on. Antacids also have a basic pH. So this all comes back to water being amphoteric. So if we write the Bronsted-Lowry acid reaction of water with water, which seems weird, but in this case one of the water molecules is going to be the acid, the other is going to be the base. What we get is one water molecule loses H+, the other one gains H+. So the one that loses H+ turns into hydroxide. The one that gains H+ turns into hydronium. So the hydronium is what makes stuff acidic. Hydroxide is what makes stuff basic. And here water is making one hydronium for every one hydroxide. So they balance each other out and become neutral. If water was instead mixed with any other acid, you would make extra hydronium and it would be acidic. If the water was mixed with a base, you would make more hydroxide and it would be considered basic. So the amount of hydronium ions produced is equal to the amount of hydroxide ions produced if we're talking about pure water. If it's any other acid or base, you'll either make more hydronium or more hydroxide. So for pure water, it has been experimentally determined that the concentration of hydroxide is equal to the concentration of hydronium, and that value is 1 times 10 to the negative 7th molar. So here's that 10 to the negative number that we were looking at back on the earlier slide about pH. So to make this more useful, we convert it into the pH scale with a log calculation. So if we look at our scale here, here's our 10 to the negative 7th that we just saw on the previous slide. Both hydronium and hydroxide have that same concentration, and notice that's when we are at neutral on the pH scale. Whenever you add acid or a base to the water, it's going to change the amount of hydronium and hydroxide you have. One's going to go up, the other is going to go down. So if you add acid, you're going to go this way on our scale. Say I added acid to where the hydronium concentration was 10 to the negative fourth. The hydroxide concentration must be 10 to the negative 10th, and vice versa. If I add base, I'm going to go up the pH scale. The base concentration is going to get bigger, say 10 to the negative second, and the hydronium's got to go smaller, 10 to the negative 12th. So this leads us to a useful equation. Hydronium concentration times hydroxide concentration is always equal to 1 times 10 to the negative 14th, which we call Kw. So what this does is allows us to go back and forth between these two concentrations. If you know one, you can always calculate the other. Here are some example problems on calculating the different concentrations using that equation that we just learned. So I'm going to rewrite it here so we can see it. The H3O plus concentration times the hydroxide concentration is always equal to 1 times 10 to the negative 14th. So this first example, we have HBr added to water, and we know the hydronium concentration is 0.03, and we want to solve for the hydroxide concentration. So to set this up, we know the hydronium, so that's the 0.03, and that times the hydroxide is equal to 1 times 10 to the negative 14th. So if we rearrange this to solve for hydroxide, we're going to have 1 times 10 to the negative 14th over the 0.03. So if you do that division, you end up with 3.3 times 10 to the negative 13th, and our concentration units are always going to be molar. And just as a note, anytime you see these square brackets, which we've been seeing, that stands for concentration of whatever is inside of the brackets. So the second problem, we know the hydroxide concentration. We want to solve for hydronium. So same idea, our unknown is hydronium. We know hydroxide is 0.006, and we know that that has to be equal to 1 times 10 to the negative 14th. So to get hydronium concentration, again, it's going to be 1 times 10 to the negative 14th over the 0.006. And if we do that math, you end up with 1.7 times 10 to the negative 12th. And again, the units are molar. To go from the hydronium concentration to pH, we're going to take the negative log of that hydronium concentration. This is base 10 log, so make sure you have a calculator that can do that function. And notice here we have to have the hydronium concentration to do this calculation. If you're given hydroxide, we just learned how we can go from hydroxide to hydronium, so we can figure that out. So if you're given hydronium and you want to get to pH, it's a one-step problem. If you're given hydroxide, first you need to go to hydronium, then you can take the negative log of that to get to pH, and so it's a two-step process. Here's a couple examples. So for each of these, we're going to calculate pH and then decide if, based on that pH, if it's acidic or basic. So first example, we're given hydronium. So all we need to do is take the negative log of that concentration. So we're going to do the negative log of 0.0089. If you punch that into your calculator, you should get a pH of 2.05. This is less than 7, so this is going to be acidic. For number 2, we're given hydroxide. So first we need to solve for hydronium and then do the negative log. So this is where the 4.9 times 10 to the negative 7th times hydronium is going to be equal to 1 times 10 to the negative 14th. If you solve for that, you should get 2.04 times 10 to the negative 8th, and that's your hydronium. Now this we can plug into the negative log. So negative log of 2.04 times 10 to the negative 8th is equal to 7.7. So our pH is just a little bit above 7, so it is considered basic. Go ahead and pause the video and see if you can calculate the pH for problems 3 and 4. All right, problem number 3. Again, we're just given hydronium, so we just need to do the negative log. So negative log of 3.5 times 10 to the negative 8th is equal to 7.5. Again, slightly above 7, so it is considered basic. Number 4, we have hydronium. We have hydroxide. So first we need to solve for hydronium. So we're going to do 0.00456. That times hydronium is equal to 1 times 10 to the negative 14th. So if we solve for hydronium, you should get 2.19 times 10 to the negative 12th. If we take the negative log of that, you should get a pH of about 11.7. This is again basic. So to measure pH, we have several different methods. You can use a pH meter, and this will give you a digital readout of pH. So you stick a probe inside of whatever your solution is. Your sample does have to be liquid, and then that will give you a pH reading on the screen. Another way to measure pH is to use litmus paper. Now litmus paper, there's two different types. There's blue litmus paper and there's red litmus paper. If you have blue litmus paper, your blue litmus paper is going to turn red if it is acidic. Your red litmus paper is going to turn blue if it is basic. Another type of tool to measure pH is using pH paper. This is paper that you again dip or put a small sample onto the paper, and it will change color based on the pH. So here's the scale. So whatever color it turns tells you what pH value your sample is. Another thing that is used to determine pH is cabbage juice. So if you boil red cabbage, it will turn the water purple. So that is neutral. If it is in something basic, it goes to kind of a blue scale all the way up to a yellow if it's very strongly basic. And then if it's acidic, it goes down to red or kind of a bright pink color. And you will see this with Wet Lab 6.